Okay, so here's where we were last time. What we were talking about last time. We were talking about this new kind of integral called vector line integrals. And I'll remind you that we have a motivation for this construction, which is a physics problem of, I want to start at A and move to B, and I want to know how much work it takes to do this. But the twists are that I'm not going in a straight line, I'm going along a curve. So I can't just say, B minus A, dot product, or something like that. And furthermore, the force that I'm having to deal with changes depending on where you are. Right, so the force is not constant and the displacement is not straight. So how do you deal with that? And this is a perfect situation to apply our what I like to, our broad brushstroke strategy is chop it up, add it up. Right, if you have a problem that doesn't really fit very well into an old formula because something's not constant, right? Then take the problem, chop it up into little pieces, such that on each piece the problem is simple, and then add up. Okay, right. So we went through those details last time. So here's the chop it up, add it up. First step in the construction. The total amount of work that it takes to move along that path is the sum of the amounts of work that it takes to move along each little piece of the path. Okay. And then on each little piece of the path, it's real simple. On a little piece of the path, the path is approximately straight and the vector field is approximately constant. So the force that we're applying is approximately constant. And this is a problem that's exactly like we saw back in chapter 1. So just dot product, right? Force dot displacement. So that leads to this Riemann sum. Well, at least this new construction that kind of looks like Riemann sums that we've written down in the past. So I'm going to call this a Riemann sum. We use integrals to shorthand Riemann sums. So when you see this expression, henceforth, you see an integral over a curve of a vector field dot a displacement, position differential. This Riemann sum is what it means. Okay. All right. So now the question: how do you compute these things? Right? How do I compute one of these line integrals? Well, we have a curve. This is a domain that we don't like. We've certainly seen before the idea that a curve is a domain that we don't like. It's dimensionally awkward. It's a one-dimensional thing in a two-dimensional world. It's not a double integral. It's not a single variable integral. So the way we resolve that is we view it as an image. We talked about this last time. View it as an image of a domain that I like better. Well, an interval on the t-axis. I like that a lot better. It's a domain for a plain old garden variety Calc 1 integral. Right? So we do a pullback, just like we've done several times before. In fact, we've already done this pullback. Right? We've done pullbacks through parameterizations with scalar line integrals. And so really, we don't have to work out new details and break new ground on, how do we work out this sort of a thing. We've already got those constructions. We just have to identify what it is we want and where it is. So what I want, now what we did previously, let me say it that way, what we did previously is we were looking at that little piece of curve and we were interested in the question of how big is this piece of curve? How long is it? What's its length? ds is what we wanted. We're looking for a size because we were computing a mass, and mass is size times density. Well, here we're not. Here we're not interested directly in size. I'm interested in displacement. I'm not interested. I don't really care about the length of dx. I care about dx itself as a vector, because on this little piece of curve, I'm going to be doing a dot product with that displacement vector. So, good news. I already know what dx is. We already have a formula for dx. It's velocity times dt. We talked about that back in the scalar line integral section. So dx, let me remind you, we're interested in computing that line integral. Dx is v dt. Just plug it in. Right? And out comes our handy-dandy formula for how to compute vector line integrals. We didn't have to, there's no new sort of instructions to create. It's just a matter of plugging in the instruction we already had. It's very handy. So here's our punchline formula, and this is where we ended class last time. This is your plug and chug formula for how to compute vector line integrals. These vector line integrals, or the way we're thinking about these vector line integrals is that we're visualizing, at least for the moment, that the vector field represents force that you're dotting with displacement to give you work. We're thinking of this as a computation of work where the integrand represents forces for the moment. And having written down the integral, here's how you compute it. Note everything on the right is in terms of t. It's an integral dt, a to b on the t-axis. This is a Calc 1 integral on the right. Okay, so let's crank one. See how this works out. Okay, we're going to walk counterclockwise along the unit circle from 1, 0 to negative 1, 0. That's our curve. Here we go. Oh, missed. There's our curve, counterclockwise along the unit circle from 1, 0 to negative 1, 0. And let's see here. We are being asked to compute the amount of work, but specifically the amount of work that it takes to walk that path where the wind is telling me I have to push a certain amount. Right? Wherever I happen to be at the point x, y, I have to push with a force opposing the wind in the amount of, well, this vector field. So that's telling me, wherever I might happen to be, how hard do I have to push? Well, with the green curve, I'm pushing with the blue forces. What's the total amount of work? Well, work is this. We're going over the green curve. Keep in mind dx is just displacement along the green curve. Blue is the force that I'm exerting. So f dot dx. I'm going to take a quick pause here. Is everybody happy with that? Very quickly, I want to comment on the minus sign, or I should say the lack of minus sign here. Why? First time we did a problem like this, we had to say, well, it was negative f dot dx. Why was there a minus sign in there? And it's all about the... Oh, sorry, go ahead. Yeah, you...
Is it because they give you the opposing force?
Yeah, exactly. So it goes down to the phrasing of the question. Here, the vector field that was given is not the force that's being applied on me. It's the force that I am applying to oppose what's being applied on me. So you're quite right. So this is given. You always got to look at the phrasing of the question and ask, when you have something that's not accelerating, but there's forces involved, well, what you have is a situation where there's multiple forces that add up to 0. So here, for example, this pen I'm holding up with my hand, there's two forces. I'm applying a force that way. Gravity is applying a force that way. They're exact negatives of each other because it's not moving. Right? So which one of those is given to you dictates whether you have to multiply by -1 to get the other one, or whether you were in fact given the one that you actually want. So look at the phrasing of the question, think it through. Which one is relevant to the question, and we're asking, how much work I have to exert. Therefore, the force we want is the force that I am pushing with, and that was what was given here. Okay. Right. Okay. So there's our integral that we want to compute. F dot dx. Now we know we have to, step 1, parameterize the curve. Again, notice that everything up here comes from the parameterization. Position is a function of time as given by the parameterization. Right? Velocity is the derivative of the parameterization. So everything on the right requires knowing the parameterization. Let's parameterize this curve. Reminder, we want to go counterclockwise along the unit circle from there to there. That easy parameterization, right? So again, we've talked about parameterizing curves previously. Make sure you're good at this. You can probably see this coming. There's a lot of parameterizing that comes up when you're computing line integrals and surface integrals. So the velocity vector is the derivative of that position parameterization, and that's an easy derivative to compute. There it is. And then it's just a matter of plugging that in Let me do it like this. Dx is VDT, which is that. Right? F of position. Well, position. Sorry, got ahead of myself. Position is the parameterization. Don't forget what the vector field is. The vector field, let's see, where was it? The vector field was given f of x comma y is negative y comma x. So if this is your x and this is your y, then that's negative y, and that's x. So here's your vector field, negative y comma x. So I'm just plugging in to the vector field formula. And now it's a Calc 1 problem. Everything in here is in terms of t. Now this one worked out really nicely. The integrand dots to exactly 1 makes for a really easy Calc 1 punchline at the end. Right? It won't always be that easy. Okay, is everybody okay with the process? See how it works? Okay, a couple more I want to do here. Same curve. Counterclockwise along the unit circle from 1, 0 to negative 1, 0. Exact same curve. By the way, therefore the exact same parameterization and the exact same velocity vector. Okay. The difference here is that we are pushing with a different opposing force. Instead of being negative yx, now f of xy is xy. So how does this change the problem? And, well, not terribly much in terms of the blunt calculation. It just means we have a different formula for the vector field here. F of xy is now xy. Velocity is the same. All the stuff preceding that step is all pretty much the same. So, of course, what happens here is that dot product ends up being 0, and not only do you get 0 as your answer then, but in fact, we're adding up a bunch of zeros. It's not that there was positive bits of work and negative bits of work that all managed to cancel somehow. Right? We added up a bunch of zeros. Now, I'd like to point to how this actually makes sense geometrically. Here's a picture of our path. There's our counterclockwise path from 1, 0 to negative 1, 0. And at a given point, x, now keep in mind the position vector for x is that vector. The field vector is also x. The field vector is the same as the position vector. That means our field vector is that. So moving along this curve, each little step that we take dx, the force is orthogonal to the direction we're moving. Right? And so, the amount of work that it takes to move along that tiny little step there is 0. Because the force is not in the direction that we're going. It's kind of like, so we talked about way back in chapter 1 the question of, how much work does it take to move this pen, how much work does it take to move this pen 1 foot? And my smart alecky answer was, I put it there and I say, well, I'm going to give it a slight nudge and just watch it go. Right? Well, the force was that way, but the displacement was that way. The orthogonality, right, is why there's no work required. It's just effortless. It just kind of goes. Right? Okay. So in this situation, as we're walking along the curve, I'm walking that way, and I'm not having to kind of lean in and push into it as I go. The wind's coming from over here, and I can just kind of lean to the right. Right, I could get myself like a kickstand with a wheel on it, just kind of hold that there so I can't fall over that way, and I'll just effortlessly walk like this. Because the direction I'm applying the force is not in the direction that I'm going. Okay. All right, here's another one. Here we're moving counterclockwise, unit circle. This time from 1, 0 to 0, 1. Now that changes the parameterization a little bit. Because we're only going to 0, 1, the parameterization starts at pi over 2. Right, so we're only going to there. We're not proceeding along to the second half. Okay. And here again, yet a different vector field representing the force that I'm having to push with. So 2, 5, different formula for the vector field. 2, 5 doesn't even depend on x and y. How convenient. Okay, this one changes the algebra that little bit. You get a different resulting dot product, therefore a different resulting integral. It's a different little Calc 1 problem. Again, this one's, pretty easy. Straightforward. Plug and chug. Make sure you can do that. And there's our result. Okay. How are we doing? Everybody happy? Okay. I'm going to give you a different way to think about these vector line integrals, and it has to do with how this construction relates to the unit tangent vector. I hope you all remember the unit tangent vector from a long time ago when we were talking about curvature. I think this is in chapter 1. Yeah. There was that series of exercises about curvature, and we defined this, the unit vector pointing in the direction of motion. We called that capital T. All right. So what does this have to do with the unit tangent vector? Do I have a, well, anyway. So this gives a different way to think about the dx vector. And keep in mind, the dx vector is our object of interest. This represents displacement. The nice thing about this dx vector, it tells you in some sense everything you need to know about the process of moving that little distance along the piece of curve. The dx vector tells you, by way of its direction, what direction is the curve going? By way of its magnitude, it tells you how long is that little piece of curve. So everything that you would want to know about that little piece of curve, how is it oriented, how long is it, it's all encapsulated in that one vector, dx. And easy to describe that vector then. Alternatively, if you were to take the unit tangent vector and multiply by this distance, ds. If you think about it, what can I say about TDS? Well, it clearly points in the same direction as dx because these are both tangent vectors. And the magnitude of TDS is ds. Same magnitude that dx has. Right? So these two vectors here have this point in the same direction and have the same magnitude, therefore the same vector. Right? So kind of convenient then, I can rewrite dx as TDS, and that allows me to rewrite the integral. Right? If I have a line integral f dot dx, I can rewrite the dx as TDS, and then move parentheses around a little bit. Right? Like so. And here's my alternative expression for a vector line integral. Integral over the curve, f dot t ds. And there's something both appealing and unappealing about this alternative version. You look at this formula here, and what's appealing about it is you say, oh, integral ds. Oh, we've already seen these. I know how to compute integral ds. That was 3 sections back, scalar line integrals. This looks like a scalar line integral. And that's appealing. Right? But I want to point out this is also a bad thing in a way, because that makes it look like this really is a scalar line integral. And I think it's important to recognize it's not really quite exactly a scalar line integral, because if you look at the integrand, this integrand here is not just a function of position. I mean, this is not like some scalar value like density or something like that. Because this, even though f is a function of position and t is a function of position, t is a function of position in a way that depends on how the curve is oriented. T is defined as the unit vector pointing in the direction the curve is going. Right? So this integrand depends on not just your location, but it also depends on the curve. Right? So scalar line integrals that we've seen in the past do not have that feature. Scalar line integrals we've seen in the past were just density is a function of location, x comma y comma z. That's it. Right? So I think it's a little bit sort of deceptive in a way to think of vector line integrals like this. Nevertheless, it is convenient for certain purposes. I'll show you one of them. One of those purposes is this vector line integral, this alternative way to write a vector line integral. Oh, I'm sorry. Keep in mind that f dot t being a unit vector, I can think of that as a component. Right. I now have a different way to think about vector line integrals. I can think about vector line integrals in relation to the component of the vector field along the curve. That's a natural object, right? Components are natural. So what does that do for us? I claim that this allows us to make an interpretation of what is a vector line integral in a different context. And I want to remind you, to this point, we had exactly one physical model for how to think about vector line integrals, and that was the integrand represents forces, and the integral itself is therefore a computation of work. So that's one application and one interpretation of what the vector field represents. Well, now, I'll remind you, we've got multiple interpretations of vector fields. The vector field might represent the flow of a fluid. I claim this is a big deal. Interpreting, vector fields as representing flows of fluids is super important. So, reasonable question. Okay, suppose I want to interpret this vector field here as representing the flow of a fluid. Now what does a line integral represent? It's not work. It's not giving me those forces anymore. So if this represents the flow of a fluid, what's that? Well, here's a way to think about it. Reinterpret the line integral like this. The component that is the integrand, easy interpretation. This just says, okay, to what extent is the fluid flowing in the same direction that the curve is going? Right? To what extent is the fluid flowing along the curve? And if this represents the extent to which the fluid is flowing along the curve at a given point, you could, loosely speaking, interpret this then as saying, look, in total along the entire curve, what's the grand total amount that the fluid is flowing along the curve? Added up over the whole curve. It's an interpretation. That's not a pre-existing idea that we've talked about. That's not like like y'all come into this class already knowing what mass is, and you come into this class, I'm going to say already knowing what work is, and if you didn't already know what was work, then certainly we could define work and then compute it. Here, we don't have a pre-existing idea of the extent to which a fluid flows along a curve, right? I'm just so this is not supposed to be a of course this has to be right. This is a how could I make reasonable physical sense out of something that I don't have a pre-existing concept? Okay. And it turns out, by the way, that this idea of understanding how much a fluid flows along a curve is something that's really interesting and useful in lots of situations. Okay. Right. Now, should you use this when you're doing a computation? Sometimes, but usually not. So let me show you why not. I'll come back here to our previous alternative. If you want to compute a vector line integral, well, this is a long way back. Here we go. If you want to compute a vector line integral, there's a formula. Plug and chug. Right? Very convenient. Everything gets in terms of t. You have a Calc 1 problem. We're real good at Calc 1 problems. Okay. So on the other hand, though, suppose I wanted to compute this not by a parameterization, but by rewriting as that. Does that help me compute it? And here's how it would break down if you did that, and I'm going to write this a little bit differently. The ds, we already know, speed times dt. That's from our section on scalar line integrals. Old news. And now let me rewrite the t vector as velocity divided by the magnitude of the velocity. That's how you find the unit vector pointing in that direction. Right, so that's that. That's just a recopy. And so look what we're actually doing. I mean, if you're trying to compute this thing, and if you say, aha, but I'm going to rewrite it like this, right? What you're doing is you're taking the given, what I was going to have to compute anyway, namely f dot v, the thing that, when you do the parameterization, that's what your integral is going to do. And I'm getting to that same conclusion. I'm just getting to it by having already had to go to the trouble of computing a magnitude, multiplying by that magnitude, and then subsequently dividing by that exact same magnitude. And they cancel, of course, and thus making this entire diversion seem kind of silly. All right, so you still get f dot v dt. So basically, if you want to do a little extra work for no benefit, you can consider this alternative. Now, that said, from a plug and chug point of view, then yeah, this is kind of silly. But there are some occasions where taking this and rewriting it like that, we might have some occasions where maybe I know some really convenient information about the unit tangent vector. If you have geometric knowledge in advance of how that unit tangent vector is behaving, this can be useful right there. And in other words, just completely bypassing all of this. That kind of stuff's going to come up. We're going to see an example of something like that later on. Okay, so that's vector line integrals. Let me just summarize. Here's the basic construction. That's a Riemann sum. This is a shorthand for a Riemann sum along each little piece of a curve. You're looking at the displacement. You're asserting that the vector field's approximately constant on that piece of curve, and vector field dot displacement. That's how you compute work, right? Natural thing, and then you add up over the entire curve. So Riemann sum construction, handy shorthand. And then alternative ways of thinking about it. This computes exactly the same thing, f dot v dt. This one's convenient computationally, right? It's set up for plugging in a parameterization. So from a computational standpoint, that's great. From a conceptual standpoint, I think that's nicer. You can see, force dot displacement is work. This really, really naturally connects to applications. So this is my favorite notation to represent line integrals. This one is the one that's most convenient for plugging and chugging, which of course there's a time for that, right? Okay. This one, if I had to choose, I would say this is my least favorite of the three, but it has its uses, right? This is the bridge to thinking about how vector line integrals can naturally connect to fluids. So this is useful as well. It's just a different point of view on, of course, the same thing. And these three different points of view are just in recognition of the fact that VDT and TDS are just different ways of writing our position differential dx. Okay. All right. Okay. So moving along. Let me write down a couple of kinds of integrals that we've talked about here before to segue into the next section. We have talked about scalar line integrals, and then we talked about scalar surface integrals, and then we defined vector line integrals. And that kind of begs the question of what are can, is there a, seems like something ought to fit into this little part of the pattern. Maybe there is such a thing as a vector surface integral. Reasonable question to ask, right? So I'm going to come at this from the point of view of a certain application, kind of like I've done for most of these other kinds of integrals. Hey, here's a specific physics problem. Let's get interested in a specific physics problem, and then it turns out that the answer to our specific physics problem is exactly the mathematical construction I want to motivate. So the answer is, yeah, there is going to be something called a vector surface integral. I'm going to motivate this by, again, not going straight at it, but talking about a physics concept first, and then in the study of and computation of that physics concept, we're going to find out that we get exactly this thing. So here's the deal. This physics concept is one you're very likely not to have seen previously. So I've got to do a little bit of talk at first about this new idea in order to motivate why I would want to do such a thing as a vector surface integral. I've got to tell you what flux is. Okay. So here's the idea. Flux says, okay, suppose we've got a vector field. Interpret your vector field as representing the flow of a fluid. So this does not represent forces. Forget about forces for the moment. Asterisk. We'll eventually return to the idea of this being forces and reinterpreting flux. But let's not. For the moment, I want to talk about fluids, only fluids. So we have these fluids flowing around. This flow of fluid, and suppose I have a surface here. Maybe the fluid is water, right? And this surface represents a net. Right? So I've got this net that I stick down in the water, and the water is flowing around. I could reasonably ask, how much water flows through the net? That's all flux is. And why I would be interested in this sort of thing? Well, maybe we're fishing, right? Maybe there's water flowing in a river. Maybe this is the flow of water in a river, and I'm out there, and I've got my net, and I stick my net down into the water, and the water is flowing through. I want to know how much water has flowed through my net, because that's where the fish are, right? And I figure if there's an average of one fish per however many thousand liters of river water. If I know how many thousand liters of river water have flowed through the net, I can estimate how many fish I have just caught. Okay. All right. Okay. Now, in order to make sense out of this, we've got to talk about which direction is the water flowing. So, again, if this is my net, and I want to know, I want to talk about the idea of flux through this surface, I have to say in what direction. So I'm going to define this as the positive direction. Now, not because it's pointing up. This is an arbitrary choice. I could just as reasonably find myself interested, for whatever reason, in how much the vector field is flowing downward through this surface, right? There's nothing magic about that. But what I'm saying is, in order to make the question really well posed, complete question, which direction is for the purposes of my question, which direction is the positive direction through my surface? And I appeal to your physics intuition. There is something fundamentally opposite about water flowing through a net in that direction versus water flowing through a net in this direction. They're opposites. Right? So I need to indicate which one's plus and which one's minus. So the unit normal vector is a way of doing that. This vector here, a unit vector, because the only thing I'm doing with this vector is defining a direction. We use unit vectors for that, and I just need it to be perpendicular to the surface. Now, let me note that when you draw an orientation, you typically, very often, might just draw one vector, but it's understood that sort of obligates you to a positive direction, that's our choice of what is a positive direction at all the other points on the surface. So when I draw the 1, you're to understand that, okay, well, it's got to be consistent, right, as you kind of move around. You couldn't have, okay, this is the positive direction at that point, and then, but you move over, and then this is the positive direction. That doesn't make any sense, right? It needs to be consistent with the surface. Okay, but absent Mobius strips or something annoying like that, we're not going to talk about any such stuff in Math 212. You draw one vector, and that indicates the answer everywhere. Okay, so here's our question. Given a surface, given a orientation, given a vector field, what's the flux? So I appeal to your, let's see, where did I guess I'll do it here. Okay, this is fine. I appeal to your intuition about how fluids flow. I'm going to break up this vector field into 2 pieces. This part that I'm going to call F perpendicular, and this part that I'm going to call F parallel. So the field vector representing the velocity of the fluid, let's say at this point, that vector has a component perpendicular to the surface, namely parallel to the normal vector. And it has a remaining component that is parallel to the surface. And there's exactly one way to do this. And so here's the appeal I want to make geometrically, and that is that I don't care about the parallel part. Right? I mean, to whatever extent the fluid is flowing along the surface, is not causing fluid to flow through the surface. If I just want to know how much fluid went from one side to the other side, how fast it's going parallel, doesn't matter. Does that make sense? Said differently, if we're in the river, right, and let's say the water's going that way, holding your net like this, you're not going to catch any fish. Right? The fish are just like, here's the fish swimming along, and he's like, hey, look at that, there's a net, and he just keeps swimming right along. Right? He doesn't get caught because he's going along it. He's not being forced into it, through it. Okay, so the extent to which the fluid is flowing parallel to the surface does not affect flux at all, is the argument that I'm making. So it's only the extent to which the fluid is going perpendicular to the surface that we actually care about. So here's the big first step formula, and that is flux. We use this letter, that's the capital Greek letter phi. Use capital Phi to avoid confusion with spherical coordinates. Okay? Capital Phi flux is proportional to 2 things. On the one hand, I'll just do it. On the one hand, how fast is the fluid flowing perpendicular to the surface component only, right? I don't care about the extent to which it's flowing parallel. The faster that it's flowing, the more water is flowing through the net. And then it's also proportional to the area. And if you have a bigger net, there's more water flowing through it. Bigger net, more fish. One way to think about it. Okay, so we're just going to call this a definition. Given a vector field flowing, this product here we're going to define as flux, and the interpretation we're going to make is, again, how much volume of fluid flows through the surface. Okay, and no surprise, the extent to which the vector field points perpendicular to the surface, that's the same as the extent to which the vector field is pointing in the same direction as the unit normal vector. That is a component, and components are computed with dot products. Okay, so this is what we're going to use day in and day out for computing flux. It's F dot N times area. Okay. Right. Now on to the next problem, and that is what if our surface is not flat? And what if our vector field is not constant? And this is a nasty problem. Here, our surface is oriented such that that's the normal vector. But the surface is curved, and so over here, that's the normal vector. So I can't just take F and just dot with the normal vector, because which normal vector? This one or that one? They're very different vectors. Right? Likewise, the vector field is not constant. Maybe the vector field is like that over there, but maybe the vector field is different in different locations. So which F do I dot? Do I dot this F or that F? They're different. Right? So we have a classical situation of we would like to compute with a simple formula, but the simple formula involves expressions that are not constant over our domain. So we will invoke chop it up, add it up. We're going to take this surface, we're going to chop it up into little pieces, and on each little piece, we're going to say, look, that piece is not exactly 100% flat, but in the limit, we're going to treat it like it's flat. And that's fine. And on that little piece, the vector field is not 100% constant, but it's just not going to change very much over that teensy-tiny little piece, certainly in the limit as n approaches infinity. And we argue that the field is approximately constant. So on this one little piece, I say the area is approximately flat. The vector field is approximately constant. And I'm going to apply exactly this formula, F dot n times area. And then we're going to add that up. So here's what that looks like. Total amount of flux. The sum of all the fluxes through all the little pieces. As in all of the previous integrals, Riemann sums that we've defined. On each little piece, there's that formula. On each little piece, it's F dot n times the area, and we already have a name for the area of a little piece of a surface. We call it delta S. Right, so component times area. This is our basic definition for the flux. And we have ourselves a brand new kind of Riemann sum. So, I've kind of lost count. Let's count Riemann sums. There's the classical single variable Calc 1 Riemann sum. Then there's the double integral Riemann sum. Then there's a triple integral Riemann sum. We had various techniques for how to compute double and triple integrals, change of variables, coordinate system integrals, stuff like that. But that's not new Riemann sum. So 3 of those. Then we have scalar line integrals, scalar surface integrals, and then yesterday we defined vector line integrals, and now today vector surface integrals. So we're up to 7 distinct kinds of Riemann sums that we've talked about so far. Yeah? Everybody good? We're going to see more as time goes on. Anyway, so this is distinct from all the different kinds of Riemann sums we've talked about in the past. It's not just a plain old double integral because our domain is a surface. But it's not like the previous kind of surface integral that we talked about. The previous kind of surface integrals were scalar surface integrals. We were computing, for example, we had a surface, and I want to know how much mass is there on the surface, and the integrand was a scalar. The integrand was a density, mass per unit area, scalar quantity. Here, our integrand is a vector field. Right? It's a very different object. So this is a new kind of a Riemann sum. And anytime we have a new kind of a Riemann sum, y'all, of course, have noticed the pattern here. Anytime you have a new kind of a Riemann sum, we come up with a new definition, a new notation, you might say, terminology for how to shorthand it. So this is just a new kind of an integral. So what I like to call a vector surface integral. So surface integral, in the sense that the domain is a surface, right? But vector surface integral because the integrand is a vector field. Okay, so vector surface integral. By the way, I sometimes call this a flux integral because, again, the big motivation for, why did I want to write down this algebraic expression in the first place? Where did this come from? What does this mean? How do I visualize it? Is understanding flux. So flux integral alternative. Okay. So flux integral. Here's an alternative notation for it. F dot NDS. This is what we've started with. That's how we compute flux. I make the observation that you can group together the N and the DS. Now, that's not how it came to us, right? It came to us as F was the vector field. It kind of was in three parts. It came to us that F was the vector field, N was the way that we computed the appropriate component, and then we multiply by ds. Here, I want to group these two things together as a single thing in ds, which I'm then going to denote by ds vector. This is just a notational choice. You don't have to do it. Plenty of textbooks don't do this at all. But I think it's super convenient for a couple of reasons. One thing is just ever so slightly less ink to write this. Right? It saves you just a couple of little pen strokes. But also it's really natural. Let's look at this object here, this ds vector that I just defined. It's in ds. If you think about what this vector is, it is really, really analogous to the dx vector. Let me remind you what we know about the dx vector when we're doing curve integrals, path integrals, line integrals. Dx vector, as I said earlier today, is a vector that tells you everything you'd want to know about that piece of curve. It points in the direction that the piece of curve is going. So the direction of dx tells you the orientation of that piece of curve. The length of the dx vector tells you how long that piece of curve is. ds does the same thing. This ds, by way of its direction, by way of the direction it's pointing, right? Keeping in mind that the direction is n's job is to describe how the surface is oriented. The direction of this ds vector is telling you, by way of the normal vector, how that little piece of surface is oriented. And the magnitude of the ds vector, we'll look at it, the magnitude of this ds vector is 1 times ds scalar. In other words, the magnitude is the area of that little piece of surface. So this one thing, this ds vector, tells you everything that you'd want to know about that little piece of the surface. Both the orientation and the size of a little piece of surface, all encoded into that one vector, the ds vector. So very analogous to the vector differential dx from line integrals. And it's compact and convenient to write down, so that's kind of nice. I also like the fact that this helps distinguish that this really is a different kind of an integral. We talked about this for line integrals. This being a no kidding, really absolutely very different kind of integral than a scalar surface integral. It's kind of unappetizing to have it look like a scalar surface integral. Right, so kind of don't like that because, again, it's not a scalar surface integral. Why would I write something down that makes it, at least in some sense, cosmetically look like a scalar surface integral? It's a little misleading. So, it's not a huge complaint, but it's, I think, undesirable. This is uniquely, apparently, a different kind of an integral, namely vector surface integral. Okay, so I like the obviousness of the notation, if nothing else. Okay, so my default notation for writing vector surface integrals is going to be like that. It's not, one can argue that this is the one that most naturally connects to the physics concept. Okay, sure, I have to agree with that, but I think this is the one that's most sort of elegant notationally. Okay, so how do we compute these things? Again, we find ourselves in a situation where, let's see, where do I, where's my picture? I have this particular picture. Yeah, here we go. Familiar situation, we have a domain here that we don't like. It's dimensionally awkward. It's a two-dimensional thing, but it's in a three-dimensional world. I can't use triple integral. I can't use a double integral. It's just, what do you do with this, right? So just like we've done before, we're going to take this thing that we don't like, and we're going to view it as being the image of something I do like. For example, hopefully, fingers crossed, a rectangle in plane, double integral territory, right? Real easy to compute these. We have all sorts of techniques. So if I can find a way to view this as an image of that, then I can do my pullback strategy and leave myself with a much more desirable integral. Okay, great. Hey, good news. We've already done this, right? We've already done pullbacks from surfaces through parameterizations back to, maybe not necessarily rectangles, but possibly rectangles. When we were doing scalar surface integrals. So I'm going to rip off, steal all of that existing construction. There's no reason to do that all over again. I already have a lot of this stuff set up. Let me just do it like this. So the edges of that rectangle, E1 du, E2 dv, their images, xu du, xv dv, those two vectors there. I already know how to compute that area, ds. Right? I already have again, this area here being ds, these vectors already being xu du, xv dv, I already have this idea of capital N. Now remember capital N? That was our notation for xu cross xv. It's a vector perpendicular whose magnitude gives you the stretching factor. And we just got through talking today about the idea of this unit normal vector. That's just a unit vector pointing in the same direction. And then we also talked about, just seconds ago, this ds vector. So this ds vector, well, it's again, it's perpendicular. It's in the same direction as little n, and therefore the same direction as capital N. It's a vector, therefore, whose direction tells you how my little piece is oriented, my little piece of area, how is it arranged. Right? But its magnitude tells you the area. Okay, so all of this, we've already created all of this. Right? And we already have formulas for how these things relate to each other. So notice all I really need here, here we go. All I need is to be able to rewrite ds. Let's go back up here to our definition. The ds vector, if I can figure out how to rewrite ds in terms of the parameterization, we're solid. This is just, f is defined at position's a function of parameters. Plug in the parameterization there. This is one thing we have to figure out, how to rewrite ds in terms of the parameterization. And we've already got it. Because ds is in ds. Let me say that a little bit more clearly. ds vector is in times ds scalar. ds scalar I've already computed. This is the result from our section on scalar surface integrals. Right? Area is stretching factor times dv. The stretching factor is the magnitude of capital N. Move the parentheses around a little bit. That becomes that. And if you think about it, what is this vector? Little n times the magnitude of capital N. Well, this vector points in the same direction as little n. Therefore, this vector points in the same direction as capital N. It has the same magnitude as capital N. It points in the same direction, has the same magnitude as capital N. It's capital N. It looks like a duck. It quacks like a duck. It's a duck. Right? I mean, because vectors are defined strictly by these two characteristics, right? Direction and magnitude. So this product, little n times magnitude capital N, shares both of these characteristics with capital N. So it's capital N. So there's our formula. ds in terms of the parameterization, right there. Capital N du dv. We already know how to compute capital N. It's a cross product. XU cross XV. This is all very plug and chug at this point. So, yeah, here it is. There's your formula. If you're interested in computing a flux, or for whatever other reason, and there will be other situations, not fluid flows, but anyway, if you want to compute a flux for whatever reason, parameterize your surface, and everything over here is computed in terms of the parameterization, right? X of u comma v is the parameterization. You're just plugging in the parameterization. That's straightforward. Capital N is the cross product of the partial derivatives of the parameterization. So again, it's computed directly from the parameterization. This then is a double integral in the UV plane. Straight up computation. All right, is everybody on board? All right, let's do an example. So we're going to look at the part of this surface that's directly above the unit disk in the XY plane. I think I have a picture of this here. Yeah, here we go. There's our paraboloid, but I want just the part that's sitting directly above the unit disk in the XY plane, so just this part of the paraboloid. So said differently, just that. There's our surface. Okay. Oriented downward. All right, so we're about to be asked to compute a flux, and specifically I'd like to know the flux through this surface in the downward direction. So for whatever reason, right, I'm interested in, there's water flowing around here, and I consider this to be the correct direction through the surface. And if fluid should happen to be flowing in this way, sort of in some sense into the paraboloid, that's backwards. That's negative flux. Right, I'm interested in what you might call outward flux. Okay. Right. Okay, and here's my vector field, and let's compute the flux. Okay, so we're going to follow the rules here. I'm going to compute the flux by parameterizing and plugging into that formula. Step one, of course, parameterize. Parameterizing is straightforward because, check it out, my surface is already written as a graph. So I can use the graph parameterization. There's the graph parameterization that unfortunately got broken up by a line break. But x and y are the parameters u and v, and then z is what the formula says it has to be. All right, and from that I can compute the capital N vector. So generic formula, xu cross xv. These partial derivatives. That's partial derivatives. You can take your parameterization, compute the appropriate partials. The cross product, that's just chapter 1 algebra. Everybody remember how to do cross products? Okay. So you did that. And there's your capital N. Now, there is I have to put a pin in this calculation for a minute and talk about a related issue that I have deliberately swept under the rug to this point because we've had enough going on in keeping track of all the different objects. We've got a new physics notion and Riemann sum construction and analogies to previous calculations. But there is an awkwardness in the phrasing of this problem that has, in fact, in a way that I haven't described yet, we've gotten a wrong answer already. We're off by a minus sign, and it's in a subtle way. So I'm gonna explain that by segueing into it with an analogy, and that is let's go back to a Calc 1 problem. I'm sorry, not a Calc 1 problem. A line integral problem, vector line integral problem. Here's a curve. Right, and I could have some vector field. Yeah. Vector field like that, let's say. And question, how much work does it take to move along this curve where you have to push, the force that you apply is given by this purple vector field. And you should be asking, but wait a second, which way? Right? Which way do you want to go? Do you want to go from the point A, whoops, I want to do this in blue. Do you want to go from the point A to the point B? Or do you want to go from the point B to the point A? Those are both reasonable questions. They both move you along this path. Right? So the question does not make sense. How much work does it take to move along this path? Unless a direction is defined on the path. Well, so we indicate directions by a unit vector. I'm going to use the unit tangent vector. By writing the unit tangent vector there, I'm telling you what is the correct direction. Which direction am I interested in? The amount of work to move along the curve. Okay, now, how does this affect your calculation? Well, it's easy. The way this affects your calculation is when you parameterize the curve, parameterize it that way. Parameterize it the way that you've been instructed to go, right? Don't parameterize it backwards. Why would you parameterize it backwards? Yeah? We want to know how much work it takes to go from A to B. Now, if you were to inadvertently, accidentally parameterize it backwards, it's how unfortunate, I guess you could say, but if you were to do this accidentally, you'd be computing the amount of work that it takes to go from B to A, and therefore at each little piece along the curve, you're going exactly in the wrong direction, which means that you're adding up a bunch of terms that are all exactly the negatives of what you're actually interested in. So, no surprise, you get exactly the negative of the answer you want. Right? Okay, so let me start this over again. To compute a vector line integral, ideally parameterize in the direction of the given orientation of the curve. Make your velocity vector point the same way as the given orientation unit tangent vector, capital T. But if you don't, if you oops it, for whatever, who knows why, maybe it's easier to parameterize backwards for whatever reason. If you parameterize it backwards, you just have to recognize, okay, well, I did it backwards, and so my answer is going to be off by a minus sign, and you can stick a minus sign in there and say, this minus sign is in recognition of the fact that I inadvertently parameterized this thing backwards. So you're off by a minus sign. Yeah, how's that feel? Everybody happy with that? Okay, so something perfectly analogous to this happens with flux integrals. Two things to observe. One is, there are two different directions along this curve. Well, likewise, with a surface, there are two different directions through the surface. You can talk about that as being the right direction through the surface, or you can talk about that as being the right direction through the surface. And if you think about it, they're exact opposites of each other. If you parameterize in such a way that your normal vector is the wrong one, you're going to get exact the negative of what you're supposed to get. Now, you could argue that just like with curves, just don't parameterize your curve backwards. Or why would you parameterize your curve backwards? Just parameterize it the way it's supposed to go. But if you do parameterize it backwards, just throw in a minus sign, right? Same with surfaces. All else being equal, it would be nice to parameterize it the right way right off the bat. But if you don't, if for whatever reason, if you end up parameterizing it backwards, just throw in a minus sign. Right? So that's the situation we actually find ourselves in here. Now look at the, again, here was our surface was this paraboloid, and we were given that on this surface, this is what we're calling the positive direction through the surface. Said differently, we want to parameterize our surface that way. We want to parameterize our surface so that the positive direction through the surface is as indicated by the given orientation. And we oopsed. Look at this. Our normal vector here that we just computed look at that third component. Our normal vector has a third component that's positive. We just computed a capital N that points somewhat up, not somewhat down. If this were negative, it would be somewhat down, right? This normal vector points somewhat up. Our normal vector that we just computed is that. So, what you would say here is that I was instructed to parameterize this surface downward, but inadvertently, accidentally, I didn't do it on purpose, it just happened, I accidentally parameterized it upward. I parameterized it in such a way that, implicit in that parameterization is that the positive direction through the surface is, inward. You maybe prefer to call it inward instead of upward. I wanted it to go outward. Okay, so two things. One, always heads up. Always think about, wait a second, what direction was I told is the orientation? What did I inadvertently, deliberately or otherwise, parameterize as my positive direction? And see if they're the same. Right? You got to check. You cannot just assume that, well, I'm writing down a parameterization, therefore the parameterization goes the correct direction. You can no more assume that than you can assume that about a curve. Just because you parameterize a curve, that doesn't mean you could be parameterizing the curve exactly backwards. You can't just make an executive decision and decide, I would like to go this way. The question gave you instructions of which way to go. So you have to check and see, did I do it forwards or backwards? Here the picture being, did I do it upside down or right side up? Might say. Right? And if you happen to have done it the correct direction, then cool, go about your business. If you, as in this case, inadvertently parameterize backwards, you get parameterized upside down here, you might say. Just don't forget to throw in a minus sign. Okay, so that's what we're going to do in this case here. We're going to recognize that this is going the wrong direction, so I'll show you how I'd write this down. I would say, oops, should be downward. So, there's the minus sign that I stick on the calculation. Everybody happy? Any questions about this? It's, kind of subtle. Okay, so don't forget to check. It is so easy to forget to check because there's so much else going on, parameterizing and derivatives and cross products and resulting dot products and integrals and a lot of other things going on. It's easy to inadvertently forget to check. That's on you to make sure to remember to check. Okay. All right, so everything else is very plug and chug. So we just got through talking about this minus sign. ds is n du dv. N, I just computed, is that. The parameterization, as usual, you just stick in there, right? So position as a function of u and v. There's your parameterization. That's our graph parameterization of our given surface. The vector field, that'll look back and remind ourselves what our formula for our vector field was. Our formula for our vector field was f of xyz equals xyz. So that turns this into that. And this is a plain old, good old garden variety double integral. At this point, you can do the dot product, but anyway, the punchline, nice, convenient double integral that you can compute by kind of whatever methods you prefer. Now, this polar coordinates works really nice in this case. Keep in mind our new domain. Here was our problem, right? We did a pullback using the graph parameterization. So that means that our new domain is just the unit disk here, UV plane. That being the unit disk, that kind of suggests polar coordinates right there, right? I mean, if you did the integral in our pullback domain, if you did this integral in rectangular coordinates, you can see there's going to be square roots involved in bounds. That means there's going to be square roots in your outer integral. The square roots and integrals are no fun, right? So polar coordinates makes this go through really nicely. Now in this case, the integrand also simplifies really nicely in polar coordinates. That's convenient as well. So this one really screams polar coordinates and easy integral to work out. Everybody happy? Okay, there's other examples here. I'm going to let y'all look at that last one there. I guess I will do this as a last example. See, how are we doing on? Now there's more stuff to say. Okay, but anyway, I want to do this last integral. This won't take very long. We should have comfortable time to do this. Compute a flux. Our surface is a sphere. Let's see, where's my picture? I guess it's down here. Yeah, here we go. Our surface is a sphere. We have a vector field given to us. Some vector field like that, and I can reasonably ask, what's the flux? Given vector field through the given surface. And look, you can parameterize and plug and chug. That would certainly work here. It would work just fine. It'd be a little bit unnecessarily clunky, though. Every so often you will get lucky, and this is a situation where it's actually very convenient to rewrite. Let me go back to one of our earlier formulations. Here we go. This flux that we're interested in computing, I can write like that. Right now, most of the time, expressing things in the language of unit vectors doesn't really have that much to. I mean, from a computational standpoint, from a parameterization standpoint, it doesn't buy you anything to do this. You're just computing magnitudes, dividing by magnitudes, multiplying by magnitudes. They cancel. It accomplishes nothing. Right? We've already made that observation. But in this case, it ends up being kind of convenient. So here's the convenience I'll note. Going back down to this new example. Yeah, here it is. Let's pass it up. Here we go. If I look at f dot n, it turns out that n is really easy to write down in this case. N comes from this picture. Here's our n vector. Think about the shape of a sphere centered at the origin. The normal vector to the surface is going to be perpendicular to the surface, but the surface is perpendicular to the position vector. So in fact, these two vectors are parallel. The normal vector to the surface and the position vector to the surface. Point the same direction. Now that's a peculiarity of spheres. Right? You get lucky in this case. Every so often something kind of cool happens. In geometrically spheres, this is something that's kind of convenient. So these two vectors point in the same direction. This one here has a magnitude equal to 3. This one here has magnitude equal to 1. And so therefore, this vector, n, is just x divided by 3. It is the position vector divided by 3. Same direction, slightly different magnitudes. Right? Well, if n is x over 3, that means I have an easy formula for its coordinates. F I have its coordinates, and so I can compute f dot n really easily. F dot n, just, there's your f, there's your n, just dot them, and you get 0. That tells you that what we've got here, these two vectors, f and n, let's see here, I think I used green here, I don't remember. F and n are perpendicular. So what I've effectively asked in this question is, compute the flux of this vector field through this surface. Yeah, but I just concluded this vector field is not cutting through the surface. It's parallel to the surface everywhere on this surface. That dot product is 0. Therefore, this integrand is 0. And therefore, the flux is 0. All right, so in this case, we got lucky, and the geometry of the situation made everything just kind of line up just so, and everything disappears in a puff of smoke. That is a coincidence. This does not happen every time. But kind of like symmetries, remember we talked about the symmetry theorems, and I claimed symmetry theorems come up surprisingly often. This kind of thing happens more than you would expect. Most of the calculations that you'll find yourself doing are not random. It's not a random vector field with a random surface. The world's full of circles. The world's full of spheres. The world's full of vector fields that look and behave in simple natural ways because that's how the universe works very often. Right, so this kind of, just fortuitous geometric coincidence. I wouldn't want to quantify and say how often, but it happens pretty often. So you definitely want to be on the lookout for these kinds of good fortunes. Save yourself a bunch of trouble. Okay, all right, so we did not finish this section today. We'll pick up here on Thursday. Don't forget, we have an exam tomorrow, and so no new material tomorrow. Also, let's see here. Now, because of the exam, between now and the exam, I don't expect you to be working on this material that we talked about today because it's not fair game for the exam, right? So your time would be best spent between now and exam time not thinking about this stuff. So effectively then the 48-hour clock for this material starts after the exam is over tomorrow, and so therefore the stuff that we just finished today is due Friday, not Thursday. All right, is everybody cool? Everybody understand the idea? Okay, great. See y'all later.